Hi everyone, welcome. Today we are going to be discussing the limit of a function. And before we start on that discussion or that lesson for the limit of a function, what I want to do is I want to first talk about the definition of a limit. That way we can go through and we can use that limit definition. So the definition on screen says, suppose f of x is defined when x is near the number a. Then we write the limit as x is approaching a for f of x is equal to L. Now we could say this as the limit of f of x as x approaches a equals to L. If we can make the values of f of x arbitrarily close to L by restricting x to be sufficiently close to a but not equal to a. Okay, so this says a lot and it says it very, very technical. And what I want to do is I want to, again, elaborate on this just a little bit more. When we're looking at the x values that are approaching some number, this is going to be that your x values approach the number 3, or the number 4, or the number 5, or the number 0, or negative pi, or negative 5, so on and so forth. And when we talk about approaching, that means that we are looking at the x values that are getting closer and closer to the number in question. Also, because we have a function f of x, as we keep getting closer and closer to the number in question, those values will have to get evaluated through the function that we are working with. Now, when we do this, we're actually creating a certain output that we want to see happen. In order to illustrate this a little bit more, I want to look at this example here that I have on screen. It says, consider your function f of x, which is x squared plus 5x plus 6, all divided by x plus 2. The domain for this function is all the real numbers except x is equal to negative 2. Simply because negative 2 would make the denominator undefined and we would have issues. Or you could say that it would make the denominator and the numerator both be 0, and then we have indeterminate form. Now, that function can be simplified. When we simplify that function, we factor the numerator, and we see that one of the factors will cancel with the factor in the denominator. So all that we're left with is x plus 3. Now we're left with this new function, x plus 3. However, x can still not be negative 2. And it cannot be negative 2, again, because at the end of the day, we started with the function f of x. Now, how does that play out, or what does that mean for us? Well, for us, what that means is the function on the left is the graph of f of x. And notice I've circled the x value of negative 2 because what I want to do is I want to investigate what is the limit as x is approaching negative 2 for my function f of x. And there's really two ways to approach negative 2. Those two ways are to approach negative 2 from the left, which we'll denote as a minus sign, and we can approach negative 2 from the right, which we'll denote as a plus sign. Assuming that we can get close and close and closer to negative 2, what we are really looking at is what are the outputs? In other words, what are the y values evaluating to as we keep getting closer and closer to negative 2? Well, notice the y values get evaluated to be 1, or to get really close to be 1. However, that value or that specific point does not exist for the function f of x. So even though the function value does not exist, this function still has a limit, and the limit is 1 as x approaches -2 for this function f of x. So we need to make sure we have that distinction, that just because a function doesn't exist at a certain x value, it doesn't mean that the limit does not exist. Now, more informally, the limit of a function, so that big technical definition that we wrote at the top of the screen, that technical definition boils down to this. The limit of a function at a point is the value the function would be at the point if it could be. So process that for a little bit. Again, we're anticipating what could this function output be. Not what is it, but what could it be if it existed. Now, aside from that, I have another example right below that that says we want to look at the limit as x is approaching -1 for my function f of x. It's the same function f of x, but now as x is approaching -1, we then get the y value of 2. And again, this is a good scenario because in this scenario, we actually get to see that the function does exist at x is equal to -1, and more importantly, the limit is defined to be 2. So now that we have this going for us, what we want to do is we want to extract a little bit more for these limits. You've seen here that we have this value that we're looking for a limit. Now, Now, we want to look at this question down below that says, estimate the value of the limit as x is approaching 0 for the function where the numerator is 4 minus the quantity of x squared, 4 minus the square root of the quantity of x squared minus 16. All of this is now divided by x squared. In order to view this, I took two different approaches. Number one, I took the approach of let's graph this. And that graph of that function is shown on the right-hand side of the screen. Now, that function, as we keep getting closer and closer and closer to 0 from the left, and as we get closer to 0 from the right, what is the overall value that the y values, or that the function, takes on? Well, you can see all of the outputs are here in green. That's actually what makes this graph, all of the outputs. And all of the outputs, as x is approaching 0, all of those outputs are approaching a certain y value. What is that y value that they're approaching? Well, in order to analyze that, we're going to go through these tables. To try to analyze that, this is the second method that I'm using here, is I am using the tabular method for limits. What I'm doing here is I am picking values that are getting closer and closer to 0. Starting on the left table, I chose the value of -1, then -0.01, negative 0.1, then -0.01, then -0.001, and then -0.0001. I inserted all of those values into my function that I'm working with. And in turn, I was able to evaluate those outputs to get me a value that's close enough to -0.125. Now again, this approach is working from the left. Okay, so here I have the approach that I'm working from the left and I'm getting closer to 0. The values for the right side, so the positive values, that is on the second table. And notice I chose very similar values from the right because again I want to investigate that topic for symmetry and I want to keep using those same values. In this particular result, I still get the exact same values to occur, which then tells me that the limit, if I want to estimate this, the limit as x is approaching 0 for my function of 4 minus the square root of x squared plus 16, all divided by x squared, that estimation will be negative 0.125. And again, I'm using that estimation. Visually, so the graph, if I was able to extract what y value do I have at this bottom peak of this graph, then I would be able to go ahead and establish that that would be negative 0.125. Versus using the tabular method, finding x values and then making those values, and then substituting those values into the function will then give me a method to try to numerically guesstimate what limit I will be looking at. So that's this example here. Let's try another example, but this one's going to be a completely visual example. For that example, I want to now investigate the limit as x is approaching 0 for sine of pi divided by x. So again, I want to approach this from the left, and I also want to approach this from the right. So from the left, we're going to be approaching 0. From the right, we're going to be approaching 0. And we're going to see what happens. So, looking at this from the left, as I start from the left, as my x values get closer and closer and closer to 0, the outputs are just the y values here. Notice, do the y values, or do the outputs, ever just converge on one specific y value? Yeah, in this case, it doesn't look like they converge to one specific y value. In this particular case, it looks like they sort of alternate between the values of 1 and negative 1. And at any given point in time, as we get closer and closer to 0 from the left-hand side, any one of those values that we pick could be either a value from 0 to 1, it could be 0, or it could be a value from 0 to negative 1. In other words, it doesn't just attain one y value. It attains many, many, many multiple values. So the limit from the left-hand side does not exist. And very similarly, you will be able to extract from the right-hand side as those values, as those x values start getting closer and closer and closer to 0, the same thing is happening. It's just bouncing around between negative 1 and 1, and it's just going up and down, up and down, up and down. The closer we get to 0, the faster that oscillation occurs. At this particular time, we can then say that the limit as x is approaching 0 for sine of pi divided by x does not exist. As an abbreviated term, we can say dne. So this limit, or this output for this function, doesn't exactly only have one output. It has many, many outputs as the function is approaching the value of 0. And again, this is where we need to be careful, because when we start analyzing these, if we take the approach of using the tabular method, we run the risk at possibly choosing the exact same values that will keep getting us, let's say, 1 or negative 1 or 0. So if I chose the values a little bit too, let's say, accurately, I might get the values of 0, 0, 0 that always occur, and in that instance, I will not get the correct value. So that is one thing that I am looking at. All right, so we get here that it does not exist. And again, we want to make sure that we start establishing what it is that we're looking at. Now, one of the things that we were then initially looking at was this, that we were talking about the left-hand limit and right-hand limit. So we were looking at the limit as x is approaching 0, and this was from the left-hand side. So I put a superscript of a minus sign on 0. This means that I'm approaching 0 from the left-hand side, and I'm still using the function sine of pi divided by x. Now, from the right-hand side, we then say that the limit as x is approaching 0, and I'm going to put a superscript on here of a plus sign. This means I am approaching 0 from the right-hand side for this function sine of pi divided by x. Now again, we came to the conclusion that either side, or the limit for either side of this function, does not exist. So we get does not exist, and we also get does not exist. Now the nice part about this is that one-sided limits, so either the left-hand limit or the right-hand limit, it's possible that one side of the limit will exist, and it's also quite possible that the other side of the limit might not exist. All right, so we have to make sure we keep that in mind. Most importantly as well is that when we are looking at some of these functions to occur, we always must break this down into left and right hand limit. And I will elaborate more on that now. So let's look at left and right hand limits. So here we're going to say that the limit as x is approaching a for f of x is equal to L. This works if and only if the limit as x is approaching a from the left-hand side of f of x is equal to L, and the limit as x is approaching a from the right-hand side of f of x is equal to L. In other words, if we want to determine whether the limit exists or not, then we need to go ahead and we need to find what is the left hand limit and what is the right hand limit. All right, so here again, formalize this. This was your left hand limit. So that was the left-hand side limit, and here's the right-hand side limit. If they both exist and if they both are the exact same number, well then we can conclude that the limit does exist, and more importantly, it is that number in question. So that's going to be super important for us, and we're going to rely on that definition as we move forward throughout the course. So one of the other items that I want to explore at this time is going to be a step function, or a piecewise defined function. So I'm going to say consider this function f of x. Whoa. There we go. So consider this function f of x. And I don't know why I said is equal to x, because it's not equal to x. So consider f of x equal to this function. This is known as your floor function. What it's going to do is it's going to take every single input and once it takes that input, it's going to round it down. So if you take an input of, let's say, 1.5, then it's going to take that 1.5 and it's going to round it down to 1. All right, so it always takes the values and it always rounds them down. So let's go ahead and let's look at a quick depiction of this. That way we can familiarize ourselves with how this function looks like. All right, so here's the function that we have. If you notice, these are all horizontal lines, and because they're horizontal lines and they're evenly spaced out this way, it has that look that it's some sort of stairs. And that's why oftentimes we refer to this as a stair function, because again, it kind of looks like stairs. But it's a piecewise defined function, where every piece that we analyze, so if we were to analyze x value of 1.5, again, the floor function will round that down to 1. If we choose 1.7, the floor function still rounds it down to 1. If we choose 1.9 for the x value, the floor function still rounds it down to 1. So it doesn't matter what value you pick between the interval, it will always round it down. Hence, it's named the floor. Now, for those of you that might be wondering, yes, there is a ceiling function. Okay, so again, there is a ceiling function, there is a floor function, but more specifically, we're working with the floor function at this point in time. Now, I'm going to make some annotations on this graph that if we ever choose 0, well then we're going to be left with 0. What happens if we choose 1? Well, when we choose 1, it has to round down to that whole number, which means it's going to round down to 1, which means we're up here. Which means this end point for this line segment from 0 to 1 actually has an open circle at 1 where y is 0. And this is because all the values that get close and close and close to 1 get rounded down to 0. However, once we actually get to 1, it rounds to 1 itself. So every left endpoint of this graph is a shaded circle, where every right endpoint is an open circle, meaning that the graph cannot attain those specific values. As such, there we are. So let's start analyzing some questions then. So we want to now find the following. Part A. We want to look at the limit as x is approaching 2 from the left-hand side for my function f of x. Part B. The limit as x is approaching 2 from the right-hand side for f of x. Part C. Find the limit as x is approaching 2 for f of x. So again, we have these three questions, and these three questions are going to be based on the function that we are observing, which is the floor function. All right, so let's work with that. Looking at part A, I want to analyze that my values for x are going to be approaching 2. They need to approach 2, and they need to be approaching from the left-hand side. So as we're approaching from the left-hand side, which function output are we closest to? It's not the y value of 0, it's not the y value of -1 or the y value of -2. As we approach 2, it's the y value of 1. In other words, the output for that function. So as we're approaching 2 from the left, we are traveling on this curve or on this function, and we are getting closer and closer and closer to which y output? Well, we're getting closer to the y output of 1. So as this function starts approaching the x values of 2 from the left-hand side, we naturally get that the limit for that function as x is approaching 2 from the left-hand side must be 1. Now let's approach this limit from the right-hand side. As we approach this limit from the right-hand side, or this function from the right-hand side, what outputs are we on? Or what outputs do we attain for these x values of 2 that are larger than 2? Well, those outputs are on y is equal to 2. More specifically, the closer we get to 2 from the right-hand side, we are actually going to be equal to the output of 2. Now, the big question now stands. Looking at part A and part B, to answer part A, if part A exists, then part A and part B must be exactly the same. So does part C exist? No, it does not. The limit does not exist. Well, why not? Well, it's not because the two left and right hand limits don't equal one another. So this limit, as my answer, does not exist. If I had to justify this, say that I had to justify this on an exam, does not exist because the left hand limit, the left hand side limit does not equal the right hand side limit. And that's all there is to it. That is how we are then analyzing what are these limits and how do we attain them and how do we observe them. Perfect. So we have this whole idea of these limits now, and that's great. So what I want to do at this point in time is I want to work on the definition of an infinite limit. So in order to do that, I will then work on the normal definition for the limit, and I'll give you an actual version or actual depiction of what it means to have these infinite limits. So by internet magic, I will make all this appear on screen in just a little bit. All right, so there we go. Internet magic. We're looking at the definition of an infinite limit. The definition of an infinite limit says that let f be a function defined on both sides of a, except possibly at a itself. Then the limit as x is approaching a for f of x is equal to infinity. This means that the values of f of x can be made arbitrarily large by taking x sufficiently close to a but not equal to a. So what does this mean for us? Well, this is what we're going to start analyzing. This here is the graph of tangent of x. So that's where I'm going to start. Okay, so all these functions that you're looking at here, this function is tangent of x. And tangent of x, we know that it has asymptotes at pi halves, 3 pi halves, 5 pi halves, so on and so forth. So what I want to do now is I want to start by observing what is the limit as my x value approaches pi halves. So it's going to approach pi halves from the left hand side, and this is going to be for tangent of x. And what is the limit as x is approaching pi halves from the right hand side, and again that's for tangent of x. Well, in order to do this, we then have to traverse on the left and on the right. So as we approach pi halves from the left side of pi halves, I am traveling along this curve. As we get closer to pi halves, this curve keeps getting larger and larger and larger and larger, which means my left-handed limit here will be approaching infinity. Now, it's kind of deceiving where the limit says that it's equal to infinity, but it really means that it grows without bound and it approaches infinity. It does not equal infinity. So again, kind of like a little misnomer there, or misvisualization there. Now, the limit as x is approaching pi halves from the right-hand side, and this is going to be for tangent of x. So again, we're approaching pi halves from the right-hand side. But from the right-hand side, I am traversing this curve, tangent, and I'm actually moving in a downward direction as my x values keep getting close to pi halves from the right-hand side. Which means, at this point in time, we have negative infinity. All right, so here's where we now get to see that infinite limits.
To solve this then?
And so this is where we now have this idea of what it means to be an infinite limit. And so, as you can see, it's typical when we have these asymptotes that we are talking about these infinite limits. And we will see this come up again when we start moving into chapter 3. So make sure you kind of keep that in mind. So I hope you all enjoyed this lesson, and stick around for the next one. I'll see you in a bit.